Okay, let's. Okay, that's good. Okay, let's get started. Today we're going to sort of wrap up some of the properties for the op amps. Last time we touched on the power supply rejection, kind of in a more abstract way, and we did the source follower. We're going to try to apply it now to our two-stage CMOS op amp, so you can see where it's coming from. And then we're going to look into some more higher gain topologies, telescopic and as well as folded. You've seen some of that, examples of some of those kind of in homeworks previously. So hopefully it's not going to be too foreign. And then next week we're going to look at some of the frequency responses for these structures. So we started talking about power supply rejection and covered the source follower. Now, in the context of our two-stage differential CMOS op amp, there are two kinds of mechanisms in which this happens. We're going to first look at how the noise feed-through happens in a configuration that's already a feedback configuration, right? So in that case, you can sort of see your circuit as being abstracted as something that we've done kind of as an example. It was this type of we called this internal amplifier, meaning being part of some switch cap circuit, for example, right? So here, my normal V out would be minus CS over CF times V in. And we said that if it's this configuration, I don't really have a bias in this node. But if this is a switch cap circuit and only part of the time it's in this configuration, part of the time the feedback is open. So we analyze what's happening with the amplifier while the feedback is being closed around it. And that's kind of this evaluation phase or charge transfer phase. And we sort of derived this expression. And then what really is happening with supply noise is that you always have these parasitic capacitances. So let's say that here you have a parasitic capacitance that couples this node to ground. And then your ground on chip is kind of noisy, right? So then you would essentially have another term here, which would be minus C supply over CF times VSS, right? Or this would be like VSS, a noise source. So essentially it's the superposition of, or it could be VDD, right? VDD. It's a superposition of this voltage and this voltage over here that gets you to the output, right? So this would be VSS or VDD. So this will be our supply noise or supply injection. Okay. If our op amp is really something like what we looked at previously, so let's say you have CS here, and here's your diff pair. Okay, let me just, instead of ground, show like this is where our noise is. And then these diff pairs, the body is also tied to this, right? Regardless of what is sitting here, whether it's a resistive load and taking things differentially or it's a current mirror, we're really interested in what happens in this feedback configuration, right? So we have this CF, which is the feedback. Somewhere here is the V out, and there's this circuit connected to some other circuit that connects to V out, right? This could be a second stage, right? So we're just interested here is how does this VSS propagate to the output through this external path. Right, that's called supply coupling. And that's happening, obviously, through this CGS1 capacitance. So if this VSS can somehow transfer itself to this node, VS, then from this node VS going out, we have essentially the same situation as from VI. I don't know what's going on. Okay, maybe we should reset it a little bit. From VI going out to VO. Right? We're just going through CGS1 rather than through CS, but it's basically the same exact mechanism. So what we can write is that VO divided by VSS is equal to the ratio VO to VS times VS over VSS. So we can now split in two gains that we're looking for. One, we're looking for how does VSS get transferred to this node, VS, and then how does VS get transferred to VO. Okay. So let's take a look at this first term, VO over VS. So we already said because of this capacitance that couples into this virtual ground node, it's the same as VI going out to VS. So this first term is going to be just minus CGS1 over CF. The second term, so this first term is due to this. The second term, VS over VSS, can anybody guess what it is? It's how we transfer from here to this point. We essentially have something that looks like the following circuit. Ground is also. And we're looking for how this gets transferred to this V output, right? Let's still call it VS just. But this should ring some bells for people who were here last time, right? Anybody remembers? So this is the same situation as with the source follower. So this was the situation with source follower, where VSS couldn't get through the source, right? So it was kind of modulating the body or the bulk terminal. This is bulk terminal. So when we wrote the small signal model for it, right here. It's the same exact situation. You have, when you're looking for the contribution of this noise, you ground the independent terminal, and then you're looking at how VSS gets through this body terminal. And the conclusion was that your VO, which is in this case in your source, over VSS was GMB over GM plus GMB. So not very good. Okay. And we said that the only way to prevent this from happening is to not make the bulk terminal be connected to the ground, but be in a separate well. So you're not connected to your common substrate, but you're actually in a separate well, which then kind of limits the choice of your transistor, because if you're in a P-epi process, you can only be in the N well, and vice versa, right? So you sort of then have to choose the type of your input transistor. Then that has some kind of ramifications in terms of the noise properties. People choose input P transistors so that they can mitigate some of the 1/F noise. And if you're tied to a P transistor, then you have to have the N well. And if you don't have the N well, then you have this problem that your input pairs are more susceptible to substrate noise, right? So there are all these trade-offs one needs to be aware when you're kind of really doing the circuit. So in this case, what we have is that this Vs over Vss is then Gm plus GmB over GmB, right? Or sorry, it's the other way around. GmB over Gm plus. Okay. So now that's from essentially this component over here. Okay. And now we can go and write up what the PSR are. We say minus because the contribution is from the VSS. And that's going to be our forward gain is just this piece, right? And then we're going to have over minus CGS1 over CF. And then we're going to have it times GM plus GMB over GMB. Of course, we can cancel this and really becomes CS over CGS1 times plus GMB over GMB. Okay. So now, in order to increase PSRR negative, you want to increase this component. And you can increase this component by making transistors smaller. So CGS, you make CGS smaller, but then you have noise implications. So we don't have yet sort of noise specifications here because it's kind of out of the scope. But that's kind of the trade-off that you're making. Now, we can, as I said, we can also, another solution is to tie M1 body or bulk terminal to source in case I don't have a separate well, right? But in that case, we said that we don't get the body effect on these transistors. And when we looked at the CMR, the input range was actually helped by having a body effect because you could have a wider range. The bigger the threshold of this transistor, kind of the bigger input range you could have. So this affects CMR goes down. So it's important that you're kind of, as we're going through this, you're kind of aware of all these causalities because when you start doing the op-amp design in the project, you will, by making these choices, whether to tie to the ground, the body to ground or to source, you will be making these trade-offs, and everything affects everything. So depending on the specs, you may have to do one thing or another. Okay, I think I used the wrong page, but doesn't matter. We'll just jump. I'll reorder. Okay, so this was. Maybe I should just label it here. So this was called like supply coupling. Example. And now we're going to just look at what happens inside the op-amp if we get, again, VDD or VSS. And it's just our normal two-stage. So we're going to first look at PSR R plus for two-stage CMOS op-amp. And so I'll draw one quickly just so we have a reference, and I'm going to start simplifying on the same schematic. So you may want to redraw multiple times. Okay, so we have something like this. We'll label this M1, M2, 3, M4, M5, M6, M7, and VO. Okay, and then here we have VDD plus this noise term, and then we have VSS plus noise term here. And just like with every situation where we have multiple noise sources, we're going to solve it by sort of doing superposition. Superposition not only in terms of, I guess, which type of PSRR we're looking for. So if we're looking at PSR RR plus, we're going to consider only VDD. But we can also split the contribution of VDD to different branches or stages in the circuit and then do it that way so that we can then assemble the whole response by superposition, make things a little bit easier. So as you'll see here, it does help. So what we're going to do in this situation, we're going to split the VDD impact to first stage versus the second stage, and then do superposition on the two. So if you look at the first stage, what I have is I'll have 1 over GM3 over there. I'll do sort of a mixed schematic here, just because I don't want to draw the whole small signal model, but you'll sort of understand what's going on. Now bias is going to be gone, so I'm just going to get RO7 here. And then these inputs are also grounded. And then from here, I'm going into the second stage. And then here, because this M6 transistor with bias being at 0, it also becomes just RO6, right, as a load. And then what I have here is I have my VDD small signal source. Now, if you take a look at this, we can do some further simplification. So I'll just use a different color for that. If you take a look at the first stage, there's really no supply voltage here anywhere, right? I have ground here, I have ground here. This VDD doesn't really feed back through the gate to the rest of the circuit. So assuming that there's a 0 voltage here as well and 0 here, I get a really, I get a unique solution, right? So what that means is that 0 voltage is also here. So this whole part of the circuit is basically completely inactive, right? So with this being the case, I can essentially go and now say, well, okay, I have I just have a situation where instead of this transistor, I will now just have also just the RO5 because the source is completely gone. So what I have here is then that the VO is equal to RO6 over RO5 plus RO6. This is VOA over VDD. Okay. So in the second example, let's just change the color. The second example, we have VDD sitting on this side and then going through, let's say, 1 over GM3 and then doing and here again, we can make this be a tail. And then from here, we have and then this is also R06. So if you take a look at what's happening here, we can sort of write by what VOB is as two stages. So VDD will first transfer to this node over here. So we have, if you see, there's some R1 impedance looking down into M1 R07. That's going to be something on the order of like GM R07. So it's pretty big. So we have a divider of VDD times R1 over 1 over GM3 plus R1. So that's voltage here, and then it gets transferred to this node by this is M1, M2, M4 by GM4 times essentially R04 in parallel with R1. And then it hits this M5, which is GM5 times R05 in parallel with R06. Okay. So this is our second stage gain. So that's this path over here. This path is, so I forgot a minus somewhere. Here and then here, right? The other path is going through the source, right? So it doesn't have this first negative sign. So we'll say plus, and then we have VDD times GM4 times R04 in parallel with R1. And then times this whole same thing. If you take a look into this, this factor here is approximately VDD because R1 is much, much larger than 1 over GM3. Right. In other words, with constant current flowing through this diode-connected transistor, its VDS is pretty constant, right? So if we take a look at this circuit over here, this VGS voltage is just dictated by the current here, okay? Because it's a diode-connected transistor. So if it's a diode-connected transistor with a constant current, then however we are fluctuating the supply, it's not really going to enter into the magnitude of this voltage. And if it's not entering into the magnitude of this voltage, then the same change here transfers to this node over here. Because the voltage is always constant. So however we're yanking the supply, that way the diode, the drain terminal follows. Well, if that happens, then that's the same thing on both sides. So it's kind of canceling out at the output of M4. Because VGS is not changing. Since VGS of M4 is not changing, you don't really have the noise coming through. See what I'm saying? So then this term and this term, because they're opposite sign, they basically cancel. So this is approximately equal to 0. Okay. So from this, what we have is that VO over VDD is VOA plus VOB over VDD. And it's approximately equal to VOA, just VOA over VDD. That was the first one. So it was R05 RO6 over RO5 plus RO6, or in other words, is RO5 in parallel with RO6 divided by RO5. As you see, this is not a very good number, right? This is almost like one, one half. So half of the supply noise makes it to the output, right? That's kind of disturbing. Okay, so if we look at the other scenario, so let's move to the next. We have PSRR minus. Then again, we're going to look at two situations. So one is going to be, again, for second stage. So we just have everything flipped. So I'm going to just draw. Now notice here, I also have this first stage, but again, as we said, it's completely inactive, right? So I have 1 over GM that's connected to and this piece also is all zeros. So I'll just draw it just for completeness. Right. And this is also grounded. So out of this transistor, the only thing that stays, again, is just RO5. And if you look at here, because VGS is 0, again, this is gone, and the only thing that remains is RO6. So the equivalent here will be RO5, oops. VOA, RO6, and then VSS. So VOA over VSS is again RO5 over RO5 plus RO6. Okay, that's for A. Uh-huh.
How come that's RO6 instead of 1 over GM6?
1 over GM6.
Because I thought if you're looking from like VSS and looking up,
Oh, okay, great question. So let's clarify that. If you look at what happened to this transistor, right? We had GM times VGS, right? But gate was shorted to source, right? And so VGS equals 0. So yes, I have my voltage VSS here, right? But gate is shorted to source, and so it's just a loop like this, right? So and then what I have in the model, I have RO6. So this current source is gone. Okay. And then the only thing that remains is RO6. So from VSS, I just see a series of two resistors, RO6 and RO5. And then I get just a resistive divider. All right. Okay, good question. So okay, let's then do the B part. So in B, we're going to feed VSS into the first stage. So and see what happens. So again, we can go through the whole thing. It will end up okay, I'll draw it just in case. But it essentially ends up being the same thing that we just discussed with the constant VDS. But let's just draw it. And then here we have RO7 and then VSS. And then from here we go into the second stage, right? And then this one is terminated by RO6. So now we're going to look at, to get VOB over VSS, we'll make it first stage, which is call this voltage. So this is VGS5. VGS5 over VSS times, VOB over VGS5. So first stage gain, second stage gain. Okay. So if you look at the first stage, we have a situation where we're feeding VSS from the bottom, and the two gates are connected to ground. This is actually equivalent to feeding minus VSS on both nodes. And then having this RO tied to ground. Right. Because it doesn't really matter where I'm moving the reference point, right? I can say I can connect these two grounds together and proclaim that this is a new node that is grounded, right? In terms of the voltage differences and potentials, it's all the same. So I'm just going to do this because it's more convenient. Why? Because now I know in what configuration this gain works, right? This is like a tail-degenerated single stage common source. Okay, so from here, what we can write is that VGS5 over VSS is exactly that. So we have our GM n times RO, or let's write it, GM1, 2. G1, RO2, RO4 over the degeneration factor, 2 times RO7, and then times GM3 times this enhancement that we get from the mirror. All right, so we can then further simplify this. RO1, RO3 is the same as RO2, RO4, GM1 and GM1. So we get something that's approximately 2 GM3 RO7. Okay. And then what we have is that, of course, the VGS5 to VSS, that's just GM5 times RO5 in parallel with RO6, or minus. Right? So the whole VOB equals GM5 times RO5 in parallel with RO6 over 2 GM3 times RO7. So let's take a look at this expression a little bit. what we have here is what is GM5 over 2GM3. And then we have RO5 in parallel with RO6 over RO7. So let's remember that when we were biasing this stuff, okay, we had I bias go here, I bias over 2 was here, and then this branch had K times I bias. That was kind of the original sizing that we did for systematic offset. So all the transistor sizes would support these bias currents. And so what will happen here is that GM5 versus GM3, their ratio would be essentially, so over 2 GM3, this ratio would be 1 over K. Or sorry, K. GM5 is bigger. K. If we look at RO5 and RO6 versus RO7, so these are all VA over I, right? So what you have is that this piece over here is VA over 2K I bias over VA over I bias. So again, this cancels out, K and K cancel out, so I really get approximately something like -1/2. Okay. Now remember, this is approximately 1/2 as well. Right? So we have a +1/2 -1/2. So VO over VSS is VOA plus VOB over VSS. And that's approximately 0. Okay, so pretty good. But we have this issue of VDD coming in, right? So PSRR plus is not really the best. Okay. So hopefully you've seen some tools how you can go about hand analyzing this. Sometimes it'll be tedious. Sometimes you can just see it more easily, like we did it in the previous one, where we kind of derived it, but then said, okay, just realizing that VDS is constant makes the noise current of the transistor M40, right? If VDS3 is always constant. Sometimes with that analysis, you can also look through. So before we sort of jump to the higher gain designs, I just wanted to do like a quick summary with a few hints of how to go about designing these two-stage CMOS op-amps. If you now go back to every single spec that we've derived, CMR, CMRR, power supply rejection ratio, input swing, output swing, all these components, and see what they depend on, you'll see one thing that's common. If we take the V overdrive and we decrease the V overdrive, which means we're reducing I bias for same W over L. Okay, we have a bunch of very beneficial things that happen, right? So first thing that's going to happen is our differential gain is going to increase. Remember, this is happening because with V overdrive reduced, our GM drops, but our R naughts increase faster, right? So that's why we get the differential gain to be better. Then we get the V output swing increases. We also get the V offset input referred decreases. We also get that CMRR increases. PSRR also increases. And input common mode range increases as well. Because we have overdrive is always a part of that equation, how much of the headroom you have, right? From both the tail source or from the top current mirror. Okay. So L is another factor that you can tweak. And with L increasing, again, a number of benefits happen. Your R naughts increase, so your gain increases. Common mode rejection increases again. It's all about output impedances of current mirrors of the current source. So you get this factor, and again, power supply rejection ratio also increases. So you may be wondering, what's wrong with this? This is great, right? I have this one factor that kills everything, right? Well, anybody knows what's wrong with this? Huh? Yeah, bingo. Gets slower. Remember, Ft was proportional to VOV over L squared. So you decrease VOV, so VOV decreases, Ft decreases. L increases, Ft decreases. With Ft decreasing, my design is slower. Okay? So this is really a sort of a fundamental trade-off. Speed versus everything else. By everything else, I mean all these other properties that we just went through in these last couple of lectures. So when you get a specification to do something in the project, you're going to have certain slew rate and speed you want to meet versus everything else, all these other specs, and you will know that you're kind of conflicted there. Okay. By changing the topology, you can start doing, getting some of these specs to be better without really sacrificing making this kind of sacrifice. And that's kind of what we're going to look at today and in the next lecture. So one example will be, as we said, to try increasing the differential gain by cascoding. So we're going to cascode the diff pair. And we also will cascode the load, the mirror. So when we do that, this is called telescopic cascode. Why, you'll see now, because it stacks like a telescope. Oh, let's just do these two internally. And then we're going to self-bias these nodes in a mirror configuration. Okay. So this is the first stage. And then we can take this and try to go into the second stage. Or we can sometimes, in some applications like switch cap and things like that, we can just use this as an op-amp. Okay? What this does in general sort of boosts the output gain. Does anybody know what the new gain should roughly be proportional to? Single stage. Previously we had, for the other one, GM times, roughly RO over 2 or something, but we'll just approximate it with GMRO, right? That was roughly our ballpark gain, right? So now with this structure, what's the new gain of the first? Yeah?
So that's squared.
Yep. It's this squared. Because it's the transconductance is still GM, but the output impedance at this node, looking up, it will be, and looking down, it will be GMRO. It's boosted by GMRO. Right? That's our classic cascode. Right? If we, for example, went with a cascode that didn't have this cascoded current mirror, but had just a single stage, right? We wouldn't be getting as high a gain because we've cascoded the diff pair, but the load looking up is still R naught. Right? So then it will be R naught in parallel with this, and that will be pretty much R naught. Right? So we need to boost both sides. That's why we had to add this stack. Okay? So yes, our new gain is GMRO squared. We could have done that by just adding simply a second common source stage, right? Because each stage has GMR naught, roughly. So why not do 3 stages instead of 2? So we just, well, the point is that whenever we do common source stage, we add a pretty significant pole. Okay? But here, if you look at this configuration, if this is going somewhere into another transistor, this point is, let's say, point B, and this is point A, then in this topology, I'll have essentially 2 poles. You know, in the pole 1 in the first stage will be related to B, and that one will be obviously the biggest. I'll have some load cap here, but it really is this R out B, which is really big, times CL or CB. This is on the order of GM RO squared, right? So that's why it's big. In in a common source, even if you were not doing the cascoding, you would be getting at least RO. So that's a pretty big, that's why the pole is big in every common source. But here, you're going to get this one plus this one, which will be dominantly like from this point over here. But that one corresponds to 1 over GM. If we label them all, it's GM of this device, right? So GMN times CA. So this is negligible. So you get sort of a less critical stability situation if you use these types of telescopics for same gain, right? As if you did kind of 2 common source stages. Okay. I'm going to delete this for now, just so I can draw the other stuff here, but you'll have it in your notes. So now we want to, if we want to still use this as just the first stage, because we want our overall amplifier to actually have larger gain than GMRO squared. Our previous 2 stage also had GMRO squared, right? So we just want to have more. Then our final stage would again be something that looks like this, obviously. But notice that if I connected this point right here, it wouldn't actually be good. Can anybody see why not? Why shouldn't I be doing this? Something that we did when we did the sizing of the 2-stage CMOS. So yeah, it's along those lines, right? the VDS on these two guys would now be dictated by the VGS of this guy, right? So there will be no way for me to guarantee the mirroring correctly, right? That the current, that this guy would be able to source the current that is some fraction of these guys. I'm getting the systematic gain error in the mirroring, because these two guys over here, this one and this one, they're diode connected, right? I want to ensure that these two guys have similar voltages across. Otherwise, I'm getting first the offset in the first stage, and then I'm transferring it also to the second stage. Right, so that's the same philosophy that we did in the single stage, where each of these transistors that were mirroring had exactly the same V overdrive. Right? So for me to do this, I need to kind of add another stage in between, but I don't want to have any gain. Okay, so I'm going to add, and I want it to have poles that are very, very far away, so that they don't really play a role. So I'm just doing a level shifter, okay? Or you can call it source follower as well. So I'm going to give it a current, and then I'm just going to level shift. So this stage here is level shifter. Source follower, this is stage 1, and this is stage 2. Okay? So now, look, I have, again, easier time doing stuff because I'm guaranteeing that the total voltage across these two guys is VGS of this guy plus VGS of this guy. Right? So I have now a similar situation that by relatively easy sizing, I can make sure that, because this is two VGS voltages as well, I make sure that this voltage is exactly the same as this voltage. Right? Oh, sorry, this is not. Okay. So we can write the total for this. We get GM times GMRO times RO, right? This is our R out B. This is approximately, so I'm not really keeping track of constants. This is our GM of the first stage. And then times this guy is a source follower, so it's approximately a 1, like GM ROP in parallel with RON over 1 plus GM ROP in parallel with RON. Because we're loading it with a current source, so that source follower is really has heavy impedance in the source, so gain is very, very close to 1. 1. And then we have our standard output here. So GMP times ROP in parallel with RON. So again, level shift minimizes systematic offset. Remember when we did the frequency characteristics of level shifters, they have pretty broad band response. So the pole is way out there because of 1 over GM. So it's really not a big deal for stability.